Because I didn't know his address, so I was like, I literally googled Theodore Pavlic address, PO box, and I saw a PDF and it was his name, and I assumed it was here. It was a PO box with his name box.
All right, let's get started. So, another announcement of an extracurricular thing. This has nothing to do with the class, though, but just in case you're interested. So I was asked to be on this panel to talk about, I guess their title is Hybrid Biotechnical Systems, and it's at this thing a week from now at 6:30 p.m. in the Marston Theater over at ISTV4, and the first 150 attendees get free food. So in case you're interested, and it's actually very Star Trek themed. I guess there's going to be an episode of Discovery that they watch, and then it goes into while there's food, and then it goes into the panel discussion. So just passing that along. This will also be posted up on Canvas. Again, no bonus credit or anything like that, other than the free food. Just if you're interested, it has nothing to do with simulation, but it's the things, this is sort of closely related to some other work that I do outside of class. So there's that, and now getting on to the class stuff. So today we'll go into Random-Variate Generation, and I've peppered in a few Lecture E1 slides that we had to skip over the last time. Basic announcements here. Homework D2 is, of course, still there. It was technically once due today, but we've got this special late policy where it's, I think, actually due Sunday with no penalty. The histogram hits are included in the homework assignment. I will mention, and I thought I had, I do have a next slide here. So if you need help with histogram stuff, there's some extra instructions I've given. The newer versions of Microsoft Excel actually make it a lot easier to generate histograms in Excel than it used to be. It used to be you had to do a lot more, especially if you're on a Mac. But now, across all platforms, it's relatively easy. I will make sort of these notes that when you're doing your histograms, already in some of the early submissions, I've seen actually several people, and this is a common mistake, maybe they just highlight the wrong column, but they'll actually take histograms of the inputs, which are those uniformly distributed random numbers, and so their histograms are just flat, going from 0 to 1. But the idea is this random variate generator that you generate will generate numbers outside of that range. So it takes the U1, the U01 numbers, and it stretches and scales them around so that they have a different range and a different shape in their distribution. So the histogram should not look like a boxcar from 0 to 1. It should look like the expected PDF from the assignment. So if you get a histogram that kind of has the shape of the PDF in the problem, then you know you did things right. If you're getting just something that's flat all the way across, you might be histogramming the wrong thing. So that's just a quick tip from taking a look at some of the early submissions. Sometimes because we do ask you to generate, whatever 1,000 samples, then people will sometimes just submit like a spreadsheet with like 1,000 numbers and expect that to be their submission. So that's, we really want the submission to be in kind of a doc format here, and it needs to be clean and legible, and ideally it should sort of be in a narrative form so the grader can follow it through and understand I'm doing this part, then I'm doing this part, and I'm doing this part, and these are the reasons why I'm doing these parts, so that we can follow through. So again, we've had some submissions in the past where people just they'll do something on pencil and paper, and there'll be different parts around different spots, and things will be circled, and that'll be it, and they'll turn that in. But if you were turning them in, on paper like up here, I think you'd sort of have a little bit of a layout that you'd be shooting for, and we're looking for the same thing here to make it easier to grade. We're grading online, we try to streamline things, but it's actually can be very difficult if it's very lightly written and all that. So there's something to keep in mind as you're putting this together is that make it almost like something you would submit at a job or something more like a report than just something you'd quickly do on a midterm or so on. Speaking of midterms, there's this ICA that's been available, so that'll be available until Thursday. Before the lecture. So that's meant to be a midterm practice lecture. Yes, question?
I have a question on the homework, actually. Yeah. So for the submission, are we allowed to do it on paper and then include the histogram from Excel?
Yeah, I'm not making any requirement that it has to be typed up or anything like that. I'm just sort of making a recommendation. But if it's it has to be clean and neat and clear. But then, so most people who've already submitted their solutions have like embedded, if they've submitted something on hand, they've embedded it within a PDF or a doc.
Yeah.
And as long as it's clear and gradable, then I'm okay with it.
Second question, for doing the ranges on the inverse transform, how do we determine if it's inclusive or not inclusive?
Well, I think we'll go over that today.
Okay.
But I think in most cases, and I think what you mean is like, if I have two ranges, do I put this point on the left or the right? If you've done it correctly, the CDF should be continuous, and it shouldn't matter which range you put it in. So they should like balance. So if you make one choice, the formula might be different, but when you actually evaluate it on the boundary, it'll come to the same number if you put it in the other one. Does that make sense?
Oh, yeah, okay.
Okay.
Yes.
So, but we will get a little bit more to that today. That's kind of what today's lecture is all about. Any other questions? Okay, so so there's a couple things here, something that might be a surprise, hopefully a positive surprise. So so we got this midterm practice thing. Thursday we'll have a midterm review. So it's basically, I've just put together some kind of what I think are the highlights of all the lectures that we've gone through, but we don't even have to get through those slides if you've got a lot of questions. There are sample midterms out there, so if you've already taken a look at the sample midterms on Canvas and you said, wow, I really didn't understand this one, can you explain to me why that's the right answer? We could fill the whole time with that. So if you have questions, bring them. Otherwise, I'll have these that are meant to sort of prompt you to give you some questions. Then we'll have the midterm, which will be basically a week from today. And then, so fortunately, we had a little bit of extra time in the semester in this class because we've managed to cap the size of the labs so that we can do all of the presentations within the labs. That freed up 2 lecture spots. As normally we have, say, 150 students. Now we only have 82. So that doesn't sound like that big of a change. But by freeing up those 2 lecture spots, it allowed me to fit in time for a midterm retake. So what we're going to do is that you will have a midterm a week from today, and then we'll have another normal lecture that Thursday week, and then you'll go away to fall break. And you'll come back from fall break, and there's only that Thursday lecture that week. That lecture will be a midterm retake. It's totally optional. Your midterm score will be the highest of these 2. It will be a different exam. It'll cover the same topics. It will be very similarly formatted, but again, it'll be different. The goal is for me to at least have the solution set almost immediately available for you for the midterm. I can't guarantee that the Scantron will come back with your grades, but it should by then. So you should pretty much know your grades by fall break. My hope is, but it just kind of depends on the backlog in Scantron. And then, if you decide that you don't want to take this exam, the mid-retake, you'll get a 0 on it, but then Canvas will automatically replace it with this one. So if you have managed to talk all the rest of your professors into letting you out of attending the rest of your, fall break classes, then you just don't even have to come this week. So that's kind of the structure here, and then we'll get back to the normal lecture schedule after that. So that's kind of the plan going forward. Are there questions about this idea of this retake? Again, it's totally optional. In fact, this one's totally optional. If you wanted to, you could skip this one and just come to the retake. We'll give you a 0 for that. But again, this will be a different exam, similar format, but both of these will be similar to the format that I've got up from last fall that's already up on Canvas. So you've already seen kind of roughly what things will look like, and you're going to see that again these 2 periods. Any questions? And then, so the goal is that other lecture, and I don't want to set this in stone yet, but I plan to actually have a final exam pre-take the week before finals week. And so basically the Thursday before finals week in this class, we'll have a 75-minute final, and then during finals week, that'll be the real final, but that's actually kind of the retake, but it sounds better to call the other one a pre-take. And then during that finals week, it'll only be a 75-minute exam rather than the full almost 2 hours. So that means that in the past, the final exam has been significantly cumulative. It'll be far less cumulative. It'll be more focused on the second. Yeah.
There are only 2 exams.
There are only 2 exams, the midterm and the final. And then, the retakes. Questions? All right, so hopefully that's clear. Hopefully that's an improvement. Okay, so yes, where we left off, we've been talking about input modeling, choosing the right models. We're going to, after the exam in Unit G, starting in Lecture G1, we're going to add a quantitative aspect to this, where you already sort of know the kind of motivation for why you would choose each one of these. But then we're going to start adding things like, all right, how do you quantitatively evaluate whether this is an exponential or a y-able? So that's sort of what we're going to add in. But for now, you should at least know the kind of qualitative differences between an exponential and a y-able and why you might choose them for different input models going into your simulation. The whole point of stochastic simulation is that you get realistic variation on the output, but you can't get variation on the output without putting variation on the input. And that's what input modeling is all about, coming up with which variation to put on the input. So once we have these input models, the question is, how do then we use a computer to generate samples from those probabilistic input models? And so the idea is, let's say I've modeled something with an exponential. So this is like a failure time of a machine, for example, or an inter-arrival time of people coming into a service. By a service, I mean like a restaurant or something like that. Then I might have some distribution of those times. And so if I convert, and I want a sample from this distribution, so ideally, I want the computer to generate outcomes that have roughly this frequency distribution. And so if I take the area underneath this curve, I then get my cumulative distribution function, and that CDF of the exponential I can use to generate these things. So if I generate random numbers from U01, and I put them in the kind of y-axis and let the CDF map me back down to the x-axis, then the uniform outcomes I started with turn into outcomes that go from 0 to infinity with this frequency distribution. And so that's the way that, so long as I have one of these available, I can use a little bit of math in order to generate samples from this distribution, and then that becomes the variation that goes into my simulation for me to generate that realistic output variation after the sim is done. So, what we answered last time was, how do we generate these things? And so how do we get the uniformity and the independence to begin with? And so we said that the simplest way and the most convenient way to do this inside a computer is to come up with deterministic mathematical expressions that mimic randomness. So this is actually closely related to things like chaos and things like that. But we want each of these sequences to be started with a seed that reliably generates the same sequence over and over again if I always start with that seed. And that allows me to then couple my simulation with a seed as a way to say, here is an example of, here's an example experiment that had a good outcome, or here's an example experiment that had a bad outcome. I can capture the entire history of the input, the entire history of my variation in a single seed. And that's what's really convenient about having these random number generators that are seeded. And so the idea here is in Excel, it's generating random numbers this way, but it doesn't give you access to that seed. And the really inconvenient thing about that, which you experience in, I think, one of your labs or your homeworks, is that when you generate a random output here, random execution, if you change something in other cells, so it updates all the cells, it then reseeds with the timer, so reseeds with the clock, and then the executions all change. And so if you manage to, you see, oh wow, I got a really weird string of events here that generated some catastrophic outcome, you basically got to screenshot that thing, because the next time you make a move or look away from Excel, it's going to regenerate a totally different set of outcomes, and you won't have that history. That's why it's convenient to have access to that seed. So in Arena, we actually do have access to the seeds. There is a seeds element in the elements panel you can drag in, and you can put your own seed up there. If you don't put your own seed in, it always starts with the same seed, but every replication will start with another seed that kind of is related to the previous seed. And so it's easy to know what seeds that they use. And the weird thing about this, when you start using Arena, is every time you open Arena and hit run on the same model, you'll get exactly the same output. And that doesn't seem good, But the reason, that's why we have replications in Arena. We can say, okay, Arena, run 10 replications, and it will guarantee that each of those 10 replications starts with a different seed. So those become 10 independent experiments that you've done, but they're replicable experiments. And so if somebody doesn't believe the outcome from experiment 4, you don't have to say, take my word for it. You'd say, fine, here's my model, here's the seed that went in with replication 4, run it yourself. And so that's kind of the purpose of having these replicable seeds, and that's why in any good simulation package, it will report the seed it uses and give you the ability to insert your own seed. Question?
Why is it always uniformly distributed between 0 and 1?
Yes, so it turns out that that is the most convenient sort of input source of noise. And so we want an input variation, and due to kind of the mathematics of probability, having a uniformly distributed random variable between 0 and 1 gives us the most flexibility in transforming it into anything else. So we can use other sources of entropy other than a uniformly distributed between 0 and 1, but it just becomes more complicated. It's much simpler if we start with a uniform. The same way as if you had a die that didn't have a uniform distribution across its faces, it becomes much more complicated to turn those outcomes into outcomes you want. Whereas if you know that they're uniformly distributed across the faces, if you needed to come up 30% of the time one outcome and 20% of the time another outcome, it's easy to sort of say, all right, faces 1, 2, and 3 are this outcome, faces 4 and 5 are that outcome, and so on. All right, so a little more info about Arena. So the random number generator in Arena has these 10, what they call streams, and streams are just Arena's way of saying these are 10 slots that each have a different seed by default. So inside Arena, without even editing the seeds, you can tell different random number processes to use a different stream, and they will necessarily draw from a different random number generator. And so inside Arena, you've got these expressions, which you also now have at least seen a little bit in lab, like unif, 0, 1, and wive, which I think, oh, maybe I didn't have wive in here, and tria, A and B, and those. So all of these random number expressions, which draw random numbers from common distributions, they usually take as their first parameters the parameters of the distribution, like the minimum and max. But there is a hidden parameter that is the stream ID. If you leave it out, it defaults to 10. But if you put it in, it's whatever stream that you want. In fact, you can go into the streams element and add your own streams. So you could create a stream called, I think I had made an example, like arrival stream. So you can say, I want all my arrivals to be a special stream that starts with a certain seed that I specify. And rather than me trying to remember that my arrival stream is stream 5, I'm just going to create a named stream called arrival stream. I want all my services to draw from a different random number generator with a different seed, and I'm just going to call that service stream. You can put those names in to these things here. So, so if you're sometimes when you look at these things like you'll see in the code, unif 12, 28, 10, and you say, what's the 10? That's weird. Like a unif should only have a min and a max. Well, that third number, that extra number, is not a parameter of the distribution. It's the stream identifier. And that shows up in anything that you do in Arena that draws from a random distribution will have an optional stream identifier. And then those streams you can edit in that streams element in the elements panel that I was talking about.
That just refers to using different seeds.
Well, yeah, each stream, so it's hard to read here, but if you went in, and we'll get into this more after the midterm, but if you edit, so in the seeds element, each of these, it says seeds here, but really these should be streams, and if you edit one of these any of these options, you get an option here that says identifier, you can type in whatever you want, seed value, any 5-digit number you want, and then it has these other options, initialize option, and we haven't talked about what those are, but I've already kind of said, like in the muffin simulation, you can have 2 different sims that you guarantee have the same muffins coming into them. Well, Arena makes it much easier to do those kind of common random numbers things, and those are these other options here. And so we'll talk about how to use those options after the midterm, but that's kind of the differentiation between a stream and a seed. A seed is just a number, but a stream is a configuration. So it's like, I want to use this random number generator with this seed, and I want you to do this special thing that makes the string operate differently than other strings. And we'll get into the details of that, but for now, just kind of think of it as a stream as kind of Arena's version of a seed. That's fine, that's a good model. All right, so that's how all this stuff gets kind of implemented in Arena. So we're not, I want you to sort of know that Arena has the ability to do this. I want you to become more familiar with these expressions like Expo and Arena, that and how they work, in fact, and know that they can be seeded as you'd like them to be seeded. But we're really focusing more of the theory on it here. So we mentioned there are two important properties of PRNGs, pseudo-random number generators. What were those two properties? And I've sort of shown them, like this is an example of one property and this is an example of another property. Independence. And so which one of these looks like, so I've noticed here's a bad example, it has clumping, and here's a bad example, there's a pattern. So which one of these is independence? Is it, how many people think this is an example, this box represents independence here? How many people think this box represents independence? Yeah, right, this is the one that demonstrates independence. And so down here, we say that these, you actually look at all of these numbers, this is the exact same list of numbers, but here, they're basically sorted, and then whenever they hit the highest number, they repeat. And so this sorted list of numbers is bad, not because it comes from sort of a bad region of the real number line. It's because you can predict that the next number will always be higher than the previous number. So there's no independence. Knowing one number restricts the probability, restricts the range of values for the next number. Question?
So it's kind of like you notice a pattern in your numbers, that's when it's bad.
That's right. Any pattern, you never want a pattern of any sort in uniformly distributed random numbers. They should just be, every time you roll a die, you want your memory of the previous die to have sort of no help in predicting the next roll. That's independence. And then uniformity is this one. So here I've got these numbers here, which were generated uniformly. So these were sort of a good example. There's nothing really to notice there. There's no pattern. Here I've kind of put colors around numbers that are close together. So if I was to give you examples to try to look for sequences that are sort of obviously bad outcomes from random number generators, here, you should notice that like all the ones in red here, 0.21, 0.19, 0.20, 0.22, 0.199, 0.202, 0.215, these all kind of cluster around 0.2. And then there's a blue clump that all kind of cluster around 0.7. And this magenta clump that all kind of cluster around 0.9. And the green one around 0.1. So at first, when you kind of step back, it looks like they're all over the number line. But if you were to plot these, you would notice clumps, and those clumps would have huge gaps in between them. So this might as well be a discrete random number generator with just a tiny little bit of noise added around it, where you're basically saying, is the outcome going to be 0.1, 0.7, or 0.2, or 0.9? And then maybe we've added just a tiny little bit of noise on top of that. So they're not uniformly distributed over the number line. And so this, in the case of die, would be like, I have a 20-sided die, but only 4 sides ever come up. So that's a violation of uniformity. So for uniformity, we mentioned 2 tests, and I'm going to skip over asking you guys about it, so we'll make sure we go over them, because we were a little late on the last lecture. But these 2 tests for uniformity are the chi-square test and the KS test. We'll go over both of those in a second. And then over here, the 2 types of tests for independence are the autocorrelation test and the runs test. And the runs test is a family of tests, and we use one particular instantiation of that in this class. So let's look at those in a little more detail. So these are our 2 tests. For large sample sizes, you use the good old-fashioned chi-square test from 380. For small sample sizes, you use the Kolmogorov-Smirnov test. For now, I'll probably, well, I don't want to say I'll tell you which test to use, but there will be sort of obvious cues as to whether you're in the small sample region or the large sample region. So let's look at the chi-squared. It's the same thing you've done in 380. I give you a bunch of data. And by the way, these tests here, of course, are much more general. In 380, you guys use the chi-squared test to do other things than test for uniformity. And after the midterm, we will use the chi-squared test to do other things as well. For now, we're using it to test for uniformity. Same thing with the Kolmogorov-Smirnov test. After the midterm, we'll use it to do things much more in general, but for now, we're just using it to test for uniformity. So the chi-squared test, you're given a string of 30 numbers. The question is, are they uniformly distributed? Do they clump in one area or not? And so we're going to divide the hypothetical interval, and that's the important thing, 0, 1. Some people, when they go on a midterm, will look for the minimum number in the 30 and the maximum number in the 30, and then they'll divide that up. But that's wrong. You want to divide the hypothetical interval. So the hypothesis, the null hypothesis, is that they're uniformly distributed on 0, 1. So we divide that interval up. And then I will, on a midterm, tell you how many intervals, subintervals to use. After the midterm, you'll start deciding on that interval number for yourself. But for now, I might say use 4 intervals, and then you would divide this 0, 1 interval into 4 equally sized intervals. 0 to 0.25, 0.25 to 5, and so on. And then you're going to count up how many outcomes go in each subinterval, and if it's uniform, it should be equal across them, or roughly equal. So the next step, count the number of observations in each class. So I can go through these 30, and I'll find 3 in this subinterval, 4 in this subinterval, 8 in this subinterval, 15 in this subinterval. Already this sort of is a flag, like just, doesn't pass the eye test. Like this is way too many in this interval here. Now that could just have happened by chance. But to me, it looks like this is probably not going to turn out well for this pseudo-random number generator. So my next question is, Sarah, well, how many would I expect? Well, if I divide 30 by 4, I would expect an average of 7.5 in each subinterval. And this is where the chi-squared assumptions come into play. This expected number of outcomes must be 5 or greater in order for us to use the chi-squared test. And we'll talk about why after the midterm. We'll talk about what we do if it's not the case after the midterm, because we don't always have to resort to the KS test. But if I tell you to use the chi-squared test on a midterm, then this will be the case. If I'm not going to force you to violate the rules. So then you have to calculate the chi-squared statistic. Again, this should be something you're familiar with 380. You just take the difference between expected and observed, square it, divide it by expected, and then add those all together for each of your subintervals, and that gives you a number. Now, in both the chi-squared test and the KS test, the statistic is a proxy for the deviation from the null expectation. So the bigger this number, the less uniform these numbers are. Same thing with the KS test. So if it's really big, then we know it's probably going to violate or not going to pass the test. And so if I look at my table, and I will give you these tables on a midterm, then I need to know, well, okay, I need to pick the right degrees of freedom. For a chi-squared test, it's the number of subintervals minus 1. And so you need for that, there's only 3 degrees of freedom when you have 4 subintervals, because once you've allocated all 3 subintervals, everybody else has to go into the 4th. So there's only 3 degrees of freedom, and that's where that 3 comes in. And then if I give you, say, well, our alpha, our type 1 error rate is 0.05, then what puts us in this column. So our threshold is 7.81. That means that a chi-squared statistic bigger than 7.81 could not have happened by chance. That's just way too big, and our null hypothesis must be wrong, and we must reject the null. If it's less than 7.81, we know nothing. We know it might, that we did not reject the null, but we can't say for certain that these numbers are uniformly distributed. But we at least have built up a little bit of confidence in that. But basically, the strongest statement we can say is we cannot reject the hypothesis of uniformity. So in this case, 7.81 is far less than 11.8667, so we reject uniformity. So I put, for brevity, reject H naught. On a midterm, I want you to be a little more explicit, because very often students learn to reject the null just by rote, but they don't really know what that means. So I want you to tell me, okay, what does that mean? So I reject the null hypothesis, and I conclude that these numbers are not uniformly distributed. Any questions about the chi-squared test applied to uniformity? Should be very similar to other examples you've done in 380, like testing for Poisson distributed things and so on. All right, so what if we have very few samples? So what if that expected number is less than 5? Or then in that case, we have to, well, at least for now, we have to resort to the KS test, the Kolmogorov-Smirnov test. And so this test works on a very different prediction from uniformity. The other test says so predictions are always if-then statements. You have a hypothesis, the numbers are uniform. If that hypothesis is true, then we can make a prediction. If we were to divide the numbers up into subintervals, then we would get an equal number in every subinterval. That is the prediction we're testing in the chi-squared test. In the KS test, we have a different prediction. The KS test, we say if we were to sort all of the numbers, then we would expect the numbers to be close to basically a subinterval. And so what we're going to say is we only have 5 numbers, and so we're going to create 5 subintervals. So we're going to create an interval for each number, which is sort of the expected place for that number. So I would have given you these numbers out of order. You would sort them. And then for 5 numbers, you divide the interval in 5. And you'd say the first number, if these are uniformly distributed, should probably fall into this first slot. The second number should fall into this second slot, and so on. There will be some numbers that fall outside of these slots, and they're going to register large differences, but that can happen. That's okay. And then the question that the KS test answers is the deviation too large to be okay? So you've got in your columns the actual data, the upper part of the expected interval, the lower part of the expected interval, and then the difference from the upper part and the difference from the lower part, all sort of made positive. And so then you take the largest difference from these rows down here, in this case it's 0.26, and then you go down here into the chi-squared table. And here the degrees of freedom are the number of data. So there are 5 subintervals. Here you don't subtract 1. It's exactly 5. And then I give you an alpha of 0.05, so your threshold is 0.565. So 0.26 is less than 0.565. So the chi-squared, or the KS test, does not have enough evidence to reject uniformity. These numbers might be uniformly distributed, but the problem here is that there's so few numbers that I don't have a lot of what we call statistical power. It may be that the reason I don't reject uniformity is just because I only have 5 numbers, and it's just not enough evidence for anything. So I can't conclude that these are uniformly distributed, but I can say that the KS test does not reject the hypothesis of uniformity. Question?
If any of those numbers are negative, you just leave them like that.
Yeah, you don't. If you notice, like in this case, 0.4 minus 0.14 gave me a positive number, but 0.14 minus 0.2 would have gotten me a negative. So if I notice that these are out of order, then basically this number is always going to be the larger of the two, and so I just go with this one. If I looked on this column here, it corresponds to this thing down here, and what we're basically saying is if this number is negative, its magnitude is going to be smaller than this difference here anyway. So if any of these look like they're going to come out negative, you can just put a little dash there. You don't even need to waste the arithmetic. All right, any questions about the KS test? It's all homework C2 stuff. All right. So then, I might ask, so this is basically, this subinterval story is one way to tell the story of the KS test. As we'll learn after the midterm, more generally what the KS test is doing is it is comparing what we call the sample CDF to the hypothetical CDF. So in the sample CDF, you plot all of your data on the x-axis against its position on the y-axis divided by the total number of samples. So 0.25 was the lowest sample, So it shows up as the first sample, and then 1 divided by 5 gives me the 0.2. 0.35 was the next one in the ordering, so 2 divided by 5 gives me the 0.4, and so on. And so here, the highest one, 0.95, shows up 5th in the ordering. Well, 5 divided by 5 is 1.0. This process of sorting your data and plotting them against their normalized rank is what we say is forming the empirical CDF. This gives us an estimation of the likely cumulative distribution function of the data. And so this is an approximation, and so this blue line is what we'd expect if these were uniformly distributed. So what the KS test is doing is it's effectively measuring the difference between these two CDFs. And if that difference is too large, we reject uniformity. If it's small enough, we don't reject uniformity. And so there's plenty of examples here where this S-shaped curve, this is actually real data that I've generated from a normal distribution. I sorted it and then I plotted it against its rank. It gave me this nice S-shaped curve, but if I plot it against a uniform distribution, there's a huge gap. So the KS test would probably reject uniformity here. Likewise, I did this with an exponential. So here's real exponential data that I sorted and plotted against its rank. And you know, it really does look like an exponential, what we would expect from an exponential, but it does not look like a uniform. So there's a huge gap here, and that would be picked up by the KS test.
Okay, so why are you comparing two different distributions?
So my question would be like, if I got data, so here I know where the data came from. If I didn't have that ground truth information, if you just gave me 1,000 numbers, and you said, are these uniformly distributed? By themselves, I don't really know if they're uniformly distributed. But if I sort them and plot them against their rank, then I can see this does not look like a uniform distribution. So if you said, here's some uniformly distributed numbers, and then I said, wait, no, there's no way these are uniformly distributed. And so what the KS test is, it makes this, goes from the qualitative, where I see the gap visually, to the quantitative, where it actually calculates the statistics of how likely this gap would be if they were uniformly distributed. Does that answer your question? Okay. So then you can do this with lots of other data here. Here's a Weibull. So this is actually a good example to show exponential and Weibull are very closely related, and yet an exponential will never be S-shaped, but a Weibull will be this nice, beautiful sigmoid shape here. And then finally, if I go, I've got now data that really was generated from a uniform distribution. And you can see that even though the data were generated from a uniform distribution, they don't perfectly land on the expected CDF just because it's random. But they roughly land on a line here, and that there is a gap. And so what the KS test is, it's going to crawl along this gap, and it will then calculate the maximum difference along this gap. And because CDFs always start at 0 and always end at 1, then they'll always match at these points, but then they'll deviate in between. And so the KS test is just measuring the maximum deviation, and then it's calculating, if the hypothesis was true, what's the maximum deviation we might expect to see for some statistical certainty, and that's the alpha value that I give.
Could you repeat what things are you graphing? Like, what are the X and Y axes?
Sure. Yeah, this is, so this in an empirical CDF, otherwise called a sample CDF, I give you like 1,000 data points, and you sort them, and you keep track of where everybody is in their sorted rank. And so each of this, this hairy line here, each one is a data point. And so this data point here is, I don't know, around 0.4. So there's some data I had that came up as 0.4. And it showed up in the ordering about 40% through the ordering. And so let's say I had 100 numbers, then 0.4 might be the 40th number. So I plot 0.4 against its rank, which would be like 40 out of 100. So every one of these, I'm just plotting the data against their sorted rank. And so, so the highest data point I got, let's say, was 0.9999. Well, it's the highest, so it shows up at 100 over 100. And that's why it gets the point up there. Any questions about that? You should all know what an empirical CDF is. That'll come up later on today, and definitely might expect questions about it on the midterm, and definitely after the midterms. Okay. All right, so then the last thing that we didn't get a quick chance to talk about much in the last lecture was testing for independence. Now, when most people talk about independence, this word autocorrelation comes up. Autocorrelation, if you break that up, auto means self, and so this is correlation with myself, or correlation with itself. And so if you take some data here, so here's samples, and here's the data values at each sample. These are the same data, but I've kind of zoomed in here. So these are maybe up to the 50th sample. And then here, I've zoomed out, and this is out to the 500th sample. And the question is, are these samples independent? So is knowing one sample gives me predictive ability to predict any other samples in the sequence? Well, that's very difficult to kind of know just by staring at it. Like, is there a pattern here or not? I don't know. So one of the methods you do to get an idea of if they're correlated or not, is you basically plot a scatter plot of data against itself after it's been shifted a certain amount. And so you can imagine taking these data, say, starting at index 0, and then you pair each data point with the next data point at index 1. And then you could plot a scatter plot of those two together and then fit a line to them and measure their correlation. And then you could do that with the data point and then the data point's 2 data points with it. So on the x-axis would be the normal data, and on the y-axis would be the data 2 data points down. And you could do that over and over and over again for every single what we call lag. And if you collected all of those together, you would get something that looks like this. And so at lag 0, that's the data correlated with itself. Well, of course, if I know a data point, I can predict that data point with 100% probability. And that's why in these correlograms, I always start at 1. So at lag 0, you have 100% correlation between the data with itself. But then at lag 1, what this is saying is there's a, say, 25% correlation. So this means that basically 25% of the variance in the next data point is predicted by knowing the previous data point. And so as I get farther out, the correlations go to 0, but then they get negative. And so this is telling me that if I know a data point here, 5 data points down, I might be able to predict by negative correlation. It means it's just going to be a positive number here is going to mean that there's very likely to be a negative number 5 data points later. And so this correlelogram is actually a much simpler way to look for patterns. So this is the correlelogram for these data. So it isn't clear here that I have a pattern, but when I do this process where I plot one against each other and I keep track of all of these correlation coefficients, then it's pretty clear I have a strong pattern, and it almost looks like there's some periodicity in here. And so when we want to kind of know, ideally what you would do is you'd say, all right, so I'm going to set a blue line here that's a threshold, and as long as every one of these correlations is under that blue threshold, then I can say that these data are independent. That knowing a data point somewhere does not give me any information about the data elsewhere. And so ideally, that would be what we want. But it turns out that it's extremely impractical to put this criteria on real data, because just because you're sub-threshold for some particular point, just by chance you might pop over the threshold. So this is a result of what we call the statistical fishing problem. You're effectively doing a hypothesis test over a huge number of tests, and eventually you're going to find a difference even when there isn't a difference. So when we talk about independence, we're often going to use is there evidence of autocorrelation? You should know that term, autocorrelation. That's just a measure of a signal's correlation with itself. So it is a measure of how much you can predict of a signal knowing past versions of that signal. But that ends up not being the test that we use when we want a statistical quantitative measure to say, is this independent or not? So the autocorrelation test will be more useful after the midterm when we talk about batching and simulation and things like that. For now, just know the word. Autocorrelation characterizes correlations between one sample in a sequence and other samples later. Yeah.
So for the plots, what was the pattern that you wanted to see?
If these were independent, there would be a spike here at lag 0, and everything else would be below these blue lines. And these blue lines, I could give you, if you look back actually in the slides for lecture E1, I give you formulas for how to calculate these blue lines based on a type 1 error rate. And so if we had a red line here, then everything else was underneath these blue lines, then we could say that this signal was independent, or all these samples were independent of each other. And we have a special name for that. It's called white noise. So if you've ever heard the term white noise, that means that every data point is uncorrelated with every other data point. The reason it's called white has to do with if you take some classes in linear algebra, you'll learn about Fourier transforms. And if you take a Fourier transform of an independent parallelogram, you'll end up getting a spectrum that's flat and thus white. So that's when, if you've ever heard the term white noise, that's where that comes from. It has to do with this parallelogram. But those are things that practically are not very useful for us when we're testing for these independencies random number generators. So you are going to use a different type of test called a runs test. So a runs test, the idea behind a runs test is you say, if these data were independent, then how many consecutive samples would we expect to share some property? And usually we define that property as, say, for example, being above the mean. So, if we happen to see a string of samples that are all above the mean, and then another string of samples that are all below the mean, and then another string of samples that are above the mean, then the question would be, how often would such strings of samples that share this property occur if these really were independent? And that's what these runs tests are about. And so in all of the runs tests, you usually convert your data, which is continuous data, so it could be anything from, say, 0 to 1, into binomial data, which will be like, has one property or has the other property. It's a 0 or a 1. It's above the mean or below the mean. And then you use effectively something like a binomial test, which you may have learned about in 380, to sort of test whether these long strings would be consistent with flipping a coin and it landing heads that many times in a row. So let me just sort of get into an example to sort of make this a little clearer. So, and I'll show a numerical example in a second, but this is the test we use in this class, the runs above and below the mean test. If you look at past midterms from other professors, they might use a different runs test. I have had students, multiple semesters, come to my midterm, and I tell them to use a runs above and below test, and I don't teach them the other runs test, but they'll do runs tests from other professors that have taught this class several semesters ago. So they've managed to teach themselves a method that I didn't even teach them, looking at old people's midterms. And that always fascinates me, and I have to give them 0 points, even though they do the test perfectly, they just did the wrong test. So do this test. So the runs above and below is the idea here is I'm going to give you a bunch of data, and I will, in this test, just for time reasons, I may actually give you the mean already. So look for the mean. If you think you need to calculate a mean of 30 numbers, I'm probably not that sadistic. So look for the mean. It may already be given to you. And then for every sample, calculate, is it above or below? So you can write a little 1 or a 0 next to the sample. It's above or below the mean. Then count the number of samples that are above and below, and that's what I did in A, the number above, in B, the number below. And then count the number of runs. And we'll see what I mean by runs here, but roughly speaking, it's a contiguous string of outcomes that are all above or all below. So if you see a bunch of a 1, 1, 1, 1, 1, 0, well then the whole string of ones is a run. And so then you count the number of those runs. And then there's a nice statistical feature that if you have a lot of data, then the number of runs will actually fall along a normal distribution with this mean and this variance. And that means we can apply a z-test. So we can effectively calculate a z-score and see if it's outside our sort of acceptable bounds. And so you'll calculate this expected mean under the hypothesis of independence. You'll calculate this expected variance under the hypothesis of independence. And then you'll calculate a z-score, the number of runs minus the expected number of runs divided by the standard deviation. So make sure you calculate, you take the square root of this thing. And then that will give you a number that you'll be able to put in a table or look at the z-score table, and I'll give you that on a midterm. And in this case, you compare, because it's a two-sided test, to the alpha over 2 level of the table, not the alpha table. So I'll say 0.05, but you're going to need to look for 0.025. And I'll show you that. So here's a numerical example that goes through all of those steps. 30 data points. I want to know, are they independent? Don't sort them, because they're almost certainly they won't be independent. Leave them in this order. So then the next step here is calculate the mean of the numbers. Again, I'll probably give this to you on a midterm, but there it is. That's the mean of those 30 numbers. I then replace every number here with a 1 if it's above the mean, or a 0 if it's at the mean or below. So now all of these numbers turned into a string of 0s and 1s. So now I can then count the number of 1s, and that's the NA value, and I can count the number of 0s, that's the NB value. And then the claim is there's 19 runs here. Where did I get that 19? Well, if I take this string of numbers here, I've now broken them out by their 19 runs. So you can see this first one, 0, 0, that's a run. It flips to 1. Well, that's a run by itself, even though it's all by itself. Another 0, 0, 1, 1. So each one of these contiguous strings, whatever it switches, then that's a new run. So I get 19 runs out of these 30 numbers. And then once I have that 19, I use those formulas that I just had there. And these, I won't give you these formulas, so it's a good thing to put on your formula sheet. So the mean and variance, I calculate those. And with that, I can take the square root of the variance to calculate a z-score. And I end up getting a number, 1.2367 is my z-score corresponding to this 19 runs. And then my question is this z-score way out of bounds for the alpha that I chose. And the alpha is 0.05, but because this is a two-tailed test, then if I give you a one-tailed critical values, you have to divide it by 2. That's why we put it into 0.025. And that has 1.96. And you should all just memorize 1.96 because it will be used over and over and over again. I mean, not just in this class, like throughout your whole career, you'll see 1.96 pop up because so many things are approximated by a normal, and so many things are tied to a 5% type 1 error rate, and so this 1.96 keeps showing up. And it's the same reason why confidence intervals are twice the size of standard errors. That twice is the 1.96. So it's a good number to know. So that's my critical value, 1.96. I calculated 1.23. 1.23 is within 1.96. And so I'm going to say I do not reject the hypothesis of independence. They might be autocorrelated, but I don't know. This test seems to say that we have no evidence to say that they are not independent. That's the runs test. Any questions about the runs test? How to calculate runs or anything like that? Okay. So expect to see these types of numerical tests on the midterms. You'll see them on the sample midterms right now. So be able to do chi-square tests, KS tests, runs tests. All right, the other thing you should be able to do is to generate numbers with the linear congruential generator. I'm not going to go over that. I think it's pretty straightforward, but be able to know this formula. This will also be something I don't give you. I hope you just sort of have that down to memory. So if I gave you these, you should be able to generate numbers in this particular way. Are there any questions about how to use the LCG to generate random numbers? A really good question, but I probably wouldn't ask because it might take too long, and it might have downstream errors if you make one mistake, is to have you generate a string of numbers and then test those numbers for independence and uniformity. So probably won't do that, but if you feel prepared to be able to do that, you'll be in really good shape. All right. So LCG properties. Know also about the combined LCG and why we use that. So the LCG is great, except it has very short cycles, or can have very short cycles. So we can combine multiple LCGs together to get very long cycles. And we need long cycles because we draw lots of random numbers in simulation. All right, so before we go on to the inverse transform stuff, any questions about the old stuff? Everything clear? All right. So okay. So you've gone in lab, you've drilled down into these processes, and there are these expressions down here. And so sometimes under this delay type, there's a bunch of standard, random variables that you often would use. But under expression here, you can put lots of other things. And so even if it's not in this list, like exponential is not in this list for the process type. It is in the list for the create type. But if you wanted an exponential, you can put in an expression for expo. But if your numbers aren't in this, if your distribution isn't in this list, then the question is, what do you do? And so that's what we're kind of addressing now, is how to build these expressions. And so, the simple case here that we kind of started out with, and I think in one of the earlier labs, is if I wanted a uniformly distributed random number between 2 and 4, we said, well, there's a simple formula for that. It's just the upper bound minus the lower bound times a uniformly distributed random number between 0 and 1 plus 2. So that gives us the idea that there should be a way for us to generate these transformations from a uniformly distributed random number between 0 and 1 and any other distribution we want. And that's what we're working on today. So the basic idea that we're starting with here is this inverse transform sampling, which is going to be kind of the widely used thing. This will be the thing you'll need to know how to do. So basically, I've got these categories here, and I don't know if I'm really going to get to the other techniques by the end of the class, but you want to make sure that you get the inverse transform method for continuous and discrete. The rest of these are just kind of there to sort of, to allow you to, for those of you that might be kept up at night wondering, what do I do when I can't use the inverse transform method? These other slides are just here to say there are other avenues, but you're not going to have to worry about doing them in this class. In other classes you will, but I just want to show you that there are some other things. So if we get there, that's great. If not, continuous and discrete inverse transform, focus on that. And so this is the basic idea. I've already kind of showed this earlier. Uniform random numbers come in, and then nice whatever distribution you want come out, and all you need is the CDF, or in particular the inverse CDF, to make this happen. So the basic idea here is if I give you a PDF, you need to be able to calculate the CDF, and I hope those of you who've done homework D2 have realized that's not as trivial as it sounds. You have to make sure, especially in these piecewise cases, you keep track of all those pieces. We'll see that in a second. Then once you have the CDF, you've got to invert it. And that also isn't always as trivial as it sounds. If you deal with squares and things like that, you got to make plus minus choices. And then, but once you invert it, and you invert it just by setting the CDF equal to R and then solving for X. And then once you invert it, you can run random numbers into the inverse transform, which is also called a quantile function. And the value that comes out will be a sample of your desired distribution. So to make that more concrete, let's say we want an exponential, and we don't have that nice expo function in Arena. Here's the PDF for an exponential. So this is the basic formula for a CDF. I need to calculate the CDF of the exponential. Well, this exponential technically has two pieces. It's 0 below 0, and it's only this nice exponential shape for 0 and above. So when I calculate my CDF, I actually have to break it into two pieces here. The negative infinity to x piece for x less than 0, and that piece all the way up to 0 plus this other piece which picks up at 0 and then takes it the rest of the way. And so fortunately, this piece is going to end up being 0, so we'll only have to worry about this piece, but we're not always that lucky. So here I've got the top piece. Well, that's just 0, and so I plugged in a 0 for both of these top pieces. And then this piece is the actual exponential that we know and love. So we plot that in, and then we end up solving, and then we end up getting this thing right here, which has got our damped exponential that we're looking for, plus the 0 over there. If hopefully that's clear. If you don't remember how to do this integration, there's like a little bit of integration by parts. I'm going to flash this up there for you to review later, but you can do this integration by parts stuff where you have a substitute variable and so on and so forth, and eventually you integrate just a normal plain vanilla exponential, which turns into another plain vanilla exponential, plug everything back in. I guess not technically by parts, just substitution. Yeah.
Are we going to have to know that for the kinds of questions we're going to ask?
Know how to integrate an exponential
Yeah.
and polynomials. That's it. Yeah, I'm not going to do trig functions. All right, so then once you've got this exponential down here, we have to invert it. So this exponential from x equals 0 to infinity maps to the PDF or the CDF from 0 to 1. So it turns out this is going to be the only part that we care about because it covers the entire CDF space. So for the exponential, the inverse here is basically needs to map from 0, 1 to 0 to infinity. So I'm going to, for that second half, I just set r equal to that damped exponential, and then I solve for x. And so so setting r equal to that, and then going down through here ends up giving me an expression here, x is equal to negative 1 over lambda, natural log 1 minus r. So that is our inverse transform generator. Yeah.
So we only do this of setting r equals to the CDF for the piecewise in which there is a function of r, not for constants.
Well, we'll get to that. It's basically where, I wouldn't say constants, it's the things that have, constants I think is a simple way to say it, right? If there's any variance in x, then that means that there is probability mass changing there, and so those are the pieces that you care about. And the other way to look at it is if you're looking at the graph, then it's only the parts where if you were to go straight over, you actually hit a piece. And so if they're horizontal here, then you kind of pass by those, and so those pieces are kind of ignored when you do the inverse. All right, so, and the triangular example will make that easier to see. So, yes, that's our inverse transform generator here. And so I just then set it equal to the quantile function, and it's just, this is just a copy of that. So that's how we solve for that. Now, a little trick is that if you were to look up in a textbook what's a generator for an exponential, they usually replace this 1 minus r with an r, and that's just a nice little optimization because if r is uniformly distributed, 1 minus r is also uniformly distributed. And so there's no reason to do this extra subtraction. So that's kind of just sort of in the back of your head, if you see this, if you think, oh, well, there must be something wrong here, I'm expecting a 1 minus r, that's where that comes from. But just, you don't have to worry about that for a midterm, but know how to do this process for the midterm. All right, and so then what do I do with that? I plug in a bunch of numbers in for that r, and I get x's out. And so that, even though my r's all go between 0 and 1, my x's go from 0 to infinity, and I get a lot more of them here than I do out here. And so it's exactly the distribution that I was expecting. Now, if I didn't have this expo inside ARENA, then what I would have to do in ARENA is implement this generator. And RA in ARENA is a shorthand for UNIF 01. So you basically take the formula you have up here and you just implement it in ARENA, and then ARENA will do the sampling for you. So if there's ever a distribution that's not in ARENA, but you have the ability to write this, you can then implement it in ARENA. Questions about this process? All right, let's look at a little more difficult one. This is the triangular distribution. So triangular distribution has a min and a max like the uniform, but it also has a mode, and it's just connected with a line in the PDF. So in the CDF, then you get this S-shaped curve, and then as in most things that are shaped this direction, the inflection point is that mode. And so we now need to then solve for this CDF in a nice analytical form or closed form, and then generate the inverse CDF. And so here's our PDF expression out here. So the CDF part here is, well, here's the definition for a CDF. I see 4 parts. So I just went out and then I wrote, for every part, I kind of then created these little, I took the first part and copied it down. The second part only shows up in the second line, the third part the third line, the fourth part the fourth line. And whenever you go from one line to the next, the x that was in the previous line becomes the limit from the previous line. So here x is less than a, so I use x, but down here x is greater than a, so this part is just ends up getting truncated just to a. And so that's where we get all these limits. And now I have to solve all of these integrals. And so I need to plug in the functions for these 4 parts. And so that's what I've done here. This first part gets a 0 all the way down through here. This last part gets a 0 down through there. And then these two need to get plugged in. So this magenta part goes in all of these 3 spots. This green part goes in these 3 spots. If I went through and keep solving that, then I'm keep collapsing these things down. And what I end up getting, so here I plugged the parts in, and if I solve this integral, so without going through the ugly details, each one of these integrals you could solve. So you expand those out and you solve them. They're just polynomials because all of the variables are in the numerator, and you end up getting these solutions here. And then I can reduce those algebraically, and then that ends up giving me my CDF. And I can check to see if it looks like a CDF by looking at its limits. And so if I look here, it starts at 0 and it ends at 1. That's good. If I were to evaluate at each one of these, like if I evaluated a, well, I should have 0 from this interval. If I evaluated a here, well, a minus a, that gives me 0 here. So at each boundary, I could sort of evaluate each section, and I find that there's no jumps. So it's a smooth, continuous function. And then, so that checks all my boxes for it being a CDF. So now I have to invert it to generate my triangular generator. And so here, I basically, like we said, I can ignore the parts that are constants. And I'm only going to focus on the parts that are non-constant. So those non-constant part are these 2 inner rows, and I can see that this first row maps from outcomes A to C to probabilities 0 to this outcome. So I could plug in a C and see what it maps to. This one maps from outcomes C to B to probabilities from this midpoint all the way to 1. And so now I just need to invert on these 2 ranges. So I just set for this range equal to R and solve, and this range equal to R and solve. If I do that, here's for the first range. So here's setting R equal to f of x, or R for this one for the first range, R equals this one for this range. And then I can go through and solve both of those at the same time. So this top one, that's this. I just set R equal to this, and I solved it on the top line. For this bottom line, I set R equal to this one and solved it on the bottom line. A little bit of algebraic substitution, I have my inverse transform generator. The trick here is that I had a square to deal with in both of these cases, which meant this square root in both of these cases had a plus or a minus in front of it. And I chose the plus and the minus here to ensure that the outcomes were in their proper spaces. And so I wanted outcomes to be between A and B. So I chose the plus here, so that's A plus a positive number. And I chose the minus here, so that's B minus a positive number. And that ensured that the outcomes stayed between A and B. All right, so are there, and then if I then run my TRIA, I end up seeing that it works. So before we move on, are there any questions about this process? Going from PDF to CDF in the piecewise fashion, and then inverting this by piece. I saw a question hand up there. That's the next slide.
It's not incorrect for on the very bottom for the range of R to have the upper bound for the first line as inclusive, and then the lower bound on the second line to be non-inclusive, right?
Right.
It doesn't matter.
It doesn't, I mean, what I mean, I wouldn't take off from this, but like if you made these both less than or equal to, and then let the reader choose, that's what. But what I was kind of shooting for here is to make sure there was no ambiguity. So this ensures that I go from 0 to 1, and there's no like I don't know which one to go to. So that's why I made this one not inclusive and this inclusive.
But if you reverse it, it wouldn't matter either way.
In this case, it wouldn't matter either way because this boundary, if you evaluate it here, is the same thing if you evaluate that here.
How did you find those intervals, updated intervals?
These intervals here?
Yes.
So these intervals come from plugging in these values. If I look at the CDF, which is back here, if I plug in a C into this, then that's where I get that first interval. Likewise, I'm going to plug a C into this, I get that same one. So we find the cut points in R space by plugging in the cut points in X space. All right, so I just want to go through. So there's this question of how would you implement this in Arena? So fortunately, Arena gives us a tree of functions, so we don't have to. But if we wanted to implement a piecewise function like this, you can do it using the logic blocks that you started to see, or you can do crazy things like this mess, and I'll zoom in here in a second. But so I can have a process like an assign block like this, and in the assign block, it does the assignments in order, so you can add these. And so I can assign a value R, a random number, and then I can create this long expression where the first piece has got a Boolean predicate in it that evaluates either to a 0 or a 1, and the second piece has got the complement of that predicate that also evaluates to 0 or 1. And so basically adding the two pieces together so that one's true, it'll only take this part, and because this will be zeroed out, and when the other one's true, this gets zeroed out, and then this one gets added in. So it's a little ugly, but I'm going to leave it. This will be on the slides online. So if you're interested, this is how you can implement. This is one of the many ways you can implement these piecewise functions inside Arena. But fortunately, for the common ones, it will automatically be doing that for us behind the scenes. Does that start to answer your question? All right. So there's a bunch of these common ones here. So I just put together a table of these inverse ones. I'm not saying you should have these available, but some people find that they have a lot of comfort in having these available just in case they end up having to invert these on the midterm and then want to make sure they've got the right formulas. In general, though, if after this class, if you have to do an inverse transform, Google for inverse CDF or the keywords quantile function. And what you'll find is that in most distributions, the quantile function is known and provided. And if you have the quantile function, you have the inverse transform generator. There's a question? Yeah.
So the purpose of it inverse transform is to generate variables into a distribution.
Yes, exactly. The desired distribution. All right, so we're kind of pushing up against time here, so I'll cover the discrete ones during the midterm review. But let's do an attendance question though. And that attendance question is, and I forgot to mention, if you have an excused absence for somehow both the midterm and the retake, just something happens or whatever, then you'll take an incomplete for the class and then take the midterm next fall. So try to attend one of the two midterms. So the question is here, is the midterm retake required? Yes or no?
What? Yeah.